Namaste students and welcome. Today we are tackling the NEB Class 12 Chemistry Inorganic section, covering Unit 6, Transition Metals, and Unit 7, Heavy Metals. In the next 20 minutes we will cover all essential concepts like complex ions, crystal field theory, color, and catalysis. We will also cover the extraction of all 5 heavy metals, copper, zinc, mercury, silver, and iron, and finish with 2 solved numericals. These 2 units together can fetch you a solid 10 to 15 marks in the NEB exam. So, let's get started. Hello students. Welcome to our one-shot on inorganic chemistry. Let's begin with Unit 6, Transition Metals. So, what are they? Transition metals are D-block elements which have a partially filled D subshell, either in their atomic state or any common ionic state. We study 3 main series, the 3D series from scandium to zinc, the 4D series from yttrium to cadmium, and the 5D series. A key point for your exams, zinc, cadmium, and mercury have a full D10 configuration. However, they are included in our NEB syllabus and studied as transition metals. Now let's discuss their general characteristics. Transition metals are typically hard, dense, and possess high melting and boiling points. They are excellent conductors of heat and electricity, which you know from everyday examples like copper wires. They readily form alloys, like brass and bronze. Chemically, 2 key properties stand out. Most are paramagnetic due to unpaired electrons, and they famously form brightly colored compounds. So why do they have these properties? It all comes down to strong metallic bonding. This strength arises because both the outer Ns and the inner N-1d electrons participate in bonding. One of the most defining chemical properties of transition metals is their ability to show variable oxidation states. This is a hallmark feature that sets them apart. The primary reason is the very small energy gap between the Ns and the N-1d orbitals. Let's look at some common examples. Iron, or Fe, very commonly shows +2 and +3 states. Manganese, Mn, is the champion here, showing a huge range of states from +2 all the way up to +7. Copper, or Cu, typically exists in +1 and +2 states. And chromium, Cr, shows important states like +2, +3, and +6. A good rule of thumb is that the maximum oxidation state possible is the sum of the 4s and 3d electrons. So, let's now break down exactly why they show these variable oxidation states. The fundamental reason is that the energies of the outermost Ns orbital and the inner N-1d orbital are very, very similar. When an atom is ionized, electrons are first removed from the outermost 4s orbital. After these are lost, removing subsequent electrons from the 3d orbital requires a very comparable amount of energy. This small energy difference allows for the removal of 1, 2, or even more d electrons, which gives rise to multiple stable oxidation states. This easy transition of electrons is the key to their chemical versatility. Hello students. Let's dive into complex ions, a key feature of transition metals. A complex ion has a central metal ion bonded to surrounding molecules or ions called ligands. Werner's theory explains this with 2 valencies. Primary valence is the oxidation state, and secondary valence is the coordination number, which is the number of ligand bonds. Ligands are electron pair donors. They can be monodentate, like ammonia, or bidentate, like ethylene. Now for some key examples. The ion tetramine-copper 2+ is written as CuNH3 4 2+. Next, hexacyanophorate 2- is written as FeCN6 4-. And finally, a simpler one, diamine silver 1+, which is AgNH3 2+. Understanding these terms is the foundation for everything that follows. Now, let's look at the shapes of these complex ions, which are determined by the coordination number. It's quite straightforward. With a coordination number of 2, the ligands spread out to form a linear shape. Our example from before, AgNH3 2+, is linear. For a coordination number of 4, 2 shapes are possible, tetrahedral, as seen in ZnNH3 4 2+, or square planar, like in NiCN 4 2-. The most common coordination number is 6, which results in an octahedral shape. Imagine ligands at the 6 points of an octahedron. Classic examples are FeCN₃ and CoNH₃. The specific shape, especially for coordination number 4, is influenced by the ligand field strength and the number of d electrons. To explain properties like color and magnetism, we use crystal field theory, or CFT. In a free metal ion, all 5 d orbitals are degenerate, meaning they have the same energy. But as ligands approach in an octahedral complex, these orbitals split into 2 energy levels. A lower energy set called T2G, which includes the dxy, dis, and dxz orbitals, and a higher energy set called Eg, containing the dx squared minus y squared and dz squared orbitals. The energy gap between them is the crystal field splitting energy, delta naught. The size of this gap depends on the ligand. Strong field ligands like Cn- cause a large split, forcing electrons to pair in the lower orbitals, creating low spin complexes. Weak field ligands like H₂SO₄ cause a small split, resulting in high spin complexes as electrons occupy the higher orbitals before pairing up. Finally, let's discuss why transition metal compounds are colored. The reason is a phenomenon called d-d electronic transition. When light passes through a complex, an electron in a lower T2G orbital absorbs a photon of a specific color and jumps to a higher Eg orbital. The color we perceive is the complementary colored light that is transmitted. For example, hydrated copper-2+ ions absorb orange light, making the solution appear blue. Other colorful examples are titanium-3+, which is purple, and manganese-2+, which is pale pink. However, some are colorless. Zinc-2+ has a full D10 configuration, while scandium-3+ has an empty D0 configuration. In both these cases, a d-d transition is impossible, so they don't absorb visible light and appear colorless. Now, let's talk about a very important property, catalysis. Why are transition metals such excellent catalysts? There are 3 main reasons. First, they show variable oxidation states. This means they can easily accept and donate electrons, acting as an electron carrier. Second, in their finely divided state, they provide a large surface area for the adsorption of reactants. And third, they form unstable intermediate complexes. This creates a new reaction pathway with a lower activation energy, which speeds up the reaction. Some crucial industrial examples you must remember are iron in Haber's process to make ammonia, vanadium pentoxide V2O5 in the contact process to convert SO2 to SO3. Nickel is used in the hydrogenation of vegetable oils. And finally, platinum in catalytic converters in our vehicles. And that brings us to the end of Unit 6. Let's do a super quick recap. We learned that transition metals are d-block elements. We discussed their key characteristics, variable oxidation states, the formation of colorful complex ions, their specific geometries or shapes based on hybridization. We touched upon crystal field theory to explain their color, and of course, their fantastic catalytic activity. Unit 6 done. Now let us jump to Unit 7, the 5 heavy metals we need to study. Before we move on, let's solve a very common numerical problem. The question is, find the oxidation state of iron in the complex FeCN₃. It's simple. First, let the oxidation state of the central metal, iron, be X. We know that each cyanide ligand, Cn, has a charge of -1, and we have 6 of them. The overall charge is -3. So, we write the equation, x plus 6 times -1 equals -3. This simplifies to x minus 6 equals -3. Solving for x, we get x equals +3. So, the oxidation state of iron is +3, which is the ferric state. As a bonus, in FeCN₃ for minus, iron would be +2, the ferrous state. Namaste students. Let's dive into Unit 7, heavy metals, starting with copper. Copper's most important ore is copper pyrites. Its chemical formula is CuFeS2. The extraction process has 4 main steps. First is concentration of the ore by froth flotation. The second step is roasting. In a reverberatory furnace, 2Cu plus O2 gives Cu2S plus 2Fs plus SO2. Third, we have smelting in a blast furnace, where we add silica as a flux. This removes iron impurities as slag, Fe0 plus CO2 gives FeCO3. The fourth step is bessemerization. Here, 2Cu2S plus 3O2 gives 2Cu2O plus 2SO2. Then, an important reaction called autoreduction occurs, 2Cu2O plus Cu2S gives 6Cu plus SO2. This produces blister copper. Finally, to get 99.9% pure copper, we use electrolytic refining. Now, let's discuss the properties of copper. It's a reddish-brown metal, famous for being highly malleable and ductile. It's also an excellent conductor of heat and electricity. One very important compound is copper sulfate pentahydrate, that is Cu-SO₄, also known as blue vitriol. Its main uses are in electroplating and as a fungicide. The major uses of copper itself include electrical wiring and making coins. It's also crucial for making alloys. Remember, brass is copper plus zinc, and bronze is copper plus tin. Let's move on to zinc. Its main ores are zinc blende, which is ZnS, and calamine, or ZnCO3. The extraction begins with concentration of the ore by froth flotation. After that, the second step is roasting. This converts the ore to zinc oxide, 2ZnS plus 3O2 gives 2ZnO plus 2SO2. The third step is reduction. We heat the zinc oxide with carbon. The reaction is ZnO plus C gives Zn plus CO. The zinc metal is distilled off as a vapor. For purification, we use electrolytic refining. The final commercial product is called spelter, which is about 97% pure zinc. Finally, let's cover the properties and uses of zinc. It is a bluish-white metal. While it's brittle at room temperature, it becomes malleable between 100 and 150 degrees Celsius. Two key compounds are zinc oxide, ZnO, known as Chinese white, which is a pigment, and zinc sulfate, ZnSO₄, known as white vitriol. What about its uses? The single most important use of zinc is galvanization, which is coating iron to prevent rusting. It is also essential for making alloys like brass, for manufacturing dry cell batteries, and in the die casting of many automotive parts. Alright class, let's move to our first heavy metal, mercury, symbol Hg. Its main ore is cinnabar, with the formula Hgs. The extraction process is simple, roasting in a current of air. The reaction is Hgs plus O2 gives Hg plus SO2. The resulting mercury vapor is then condensed to get the liquid metal. Mercury's properties are quite unique. It's the only liquid metal at room temperature, it's silvery white, and has a very high density of 13.6 grams per cubic centimeter. Remember two key compounds, mercuric chloride, HgCl2, also called corrosive sublimate, and mercurous chloride, Hg2Cl2, known as calomel. Mercury is used in thermometers, barometers, dental amalgams, and fluorescent lamps. Next up is silver, symbol Ag. Silver's most common ore is argentite, or silver sulfide, Ag2S. It is also recovered from the anode mud of copper refining. For extraction, we use a very important method, the MacArthur Forest cyanide process. This is a two-step process. In step 1, the concentrated ore is leached with a dilute sodium cyanide solution. The reaction is Ag2S plus 4 NaCN gives 2 NaAgCN2 plus Na2S. This forms a soluble complex. In step 2, we perform displacement by zinc. We add zinc scraps to the solution, and the reaction is 2 NaAgCN2 plus Zn gives Na2ZnCN4 plus 2 Ag. This precipitates the silver. This crude silver is then purified by electrolysis. Let's wrap up with the properties and uses of silver. Silver is a beautiful, lustrous white metal. A very important fact to remember is that it is the best conductor of heat and electricity among all metals. This property makes it very valuable. Let's look at its compounds. First, we have HNO₃, silver nitrate, which is also known as lunar caustic and is widely used in silver plating. Then we have silver bromide, AgBr, and silver chloride, AgCl. These two are light sensitive, which is why they are essential in making photographic films. Finally, the uses of silver are quite well known in jewelry and coins, for mirror making, in photography, and as electrical contacts in high-end electronics. NEB students, let's cover the extraction of iron. Iron is extracted from ores like hematite, which is red Fe2O3, and magnetite, which is black Fe3O4. This happens in a blast furnace. At the bottom, the zone of combustion is at 1500 degrees Celsius, where C plus O2 gives CO2. This hot gas rises. In the middle, CO2 plus C gives 2CO, our main reducing agent. Also in the middle is the zone of slag formation. Limestone, KCO3, decomposes to KO plus CO2. Then, KO plus CO2 gives KCO3, which is the slag. In the upper zone of reduction, around 700 degrees Celsius, the iron ore is reduced. Fe2O3 plus 3CO gives 2 Fe plus 3CO2. The product is pig iron containing about 4% carbon, which is brittle. The brittle pig iron is refined into steel, which is an alloy of iron with 0.1 to 2% carbon. One key method is the Bessemer process, where a blast of hot air is blown through molten pig iron in a Bessemer converter to oxidize and remove impurities. Another method is the open hearth process, which uses a reverberatory furnace with a charge of pig iron plus scrap iron plus hematite. Steel is classified by carbon content. We have mild steel with 0.1 to 0.3% carbon, medium steel 0.3 to 0.7%, and high carbon steel 0.7 to 1.5%. A very important alloy is stainless steel, containing iron plus 18% chromium plus 8% nickel, making it highly corrosion resistant. Now, the rusting of iron. This is a slow electrochemical oxidation process. Two conditions are essential, both moisture, H2O, and oxygen, O2. According to the electrochemical theory, a spot on the iron surface acts as an anode, where iron oxidizes, Fe gives Fe2++ 2 electrons. At another spot, the cathode, oxygen is reduced, O2 plus 2 H2O plus 4 electrons gives 4 hydroxide ions. The Fe2+ is further oxidized to Fe3+, finally forming hydrated iron 3 oxide, Fe2O3.X H2O, which is rust. To prevent rusting, we can use methods like painting, galvanization with a zinc coating, electroplating, alloying as in stainless steel, and cathodic protection using sacrificial anodes. All right, let's solve a typical numerical problem. The question is, calculate the mass of iron that can be extracted from 100 kilograms of iron ore containing 80% Fe2O3. First, let's identify what's given. We have 100 kilograms of ore, and purity is 80%. Step 1, find the actual mass of Fe2O3. This is 80% of 100 kg, which is simply 80 kg. Step 2, we need the molar mass of Fe2O3. That's 2 times 56 for iron, plus 3 times 16 for oxygen. This is 112 plus 48, which equals 160 grams per mole. Within this 160 grams, the mass of iron is 112 grams. Step 3, now we calculate the mass of iron. We use the ratio, the fraction of iron in the compound, which is 112 by 160, multiplied by the total mass of the compound, 80 kg. So, the calculation is 112 divided by 160 times 80 kg. This is 0.7 times 80 kg. The final answer is 56 kg of iron. And that's a wrap on our inorganic chemistry one-shot. We covered Unit 6 on transition metals, including complex ions, shapes, and crystal field theory. Then in Unit 7, we saw the extraction of iron, copper, and silver. Remember the key iron extraction reaction, Fe2O3 plus 3CO gives 2 Fe plus 3CO2, and the crystal field splitting diagram. If this video helped your revision, subscribe and like. Drop a comment for the next chapter you want. Organic Chemistry one-shot coming next, stay tuned.